now. Okay, so it is recording, not the audio. If for whatever reason, this class is small enough that if for whatever reason you've fallen behind and you haven't submitted a homework, just email it to me, okay? I'll take a look at it. So no problem here, but just make sure you're doing your assignments. Don't miss any points. I think most of you did a great job on the homework. All right, so let's go ahead and I think I have the Jupyter here. So I'm going to share. All right, so I should be sharing the last. So I think we were working on Numpy examples. Right, so this is the one. So you should be seeing the Numpy examples Jupyter notebook that we were working on last week. So as you remember, we were doing all of this. We went over, we're just becoming familiar with matrices and vectors, and this is a good exercise to go through. And usually what I do, whenever I forget, I just go back to this. I always do these exercises, and I find them very, very helpful. They just remind me. I provided the link for these on Brightspace, so you can just check them out there. Okay. All right. So we were looking at, oh yeah, indexes, right? So not slicing yet, but just indices and extracting data via index from something. We looked at distributions, right? So we looked at the normal distribution with a mean of 0 and a standard deviation of 1. So that's up here, right? And then we looked at the identity matrix, which we will see later on as we start doing some operations. This identity matrix becomes useful once you get into algorithms like KNN, and you're like, oh, how would I do this? And then, a multiplication with a identity matrix does the job, that kind of thing. So it's very useful. Then we looked at dimension, shapes, data type. Oh, before I continue, I guess I should have asked, are there any questions, guys? Any questions?
No questions.
All right, great. So then we got as far as indexing last week. And we looked at, third, last, first, before last, and so on. So that's as far as we got. All right, so today let's do a few more examples. These examples now would involve extracting data from not vectors, but matrices, right? So if you notice here, we just had a vector, this one. Now we're going to have, a matrix basically. Let's call it A, numpy.array. Okay. And now notice that, we're going to define an object made up of basically 3 rows, right? So a matrix. So I'm going to do it like this. Like this, so you can see how it aligns basically. Oops. Okay. All right, and then now here we can add our vectors. So I'm going to add the first one. 1, comma, 2, comma, 3, comma, 4. And then notice the comma here, right? So that allows me now, within this set of brackets, to add all the vectors that I want. Okay, so all right. Okay, so let's look at the next one. Just hit enter. Yeah, that's good. I don't know why these are not aligning so well. Okay. So Jupyter notebooks are a little. Okay, so 5, squirrely, 6, 7, and then 8. Okay, so now comma. Okay. And this is going to be 9, comma 10, comma 11, 12. All right, so that should do it. And then let's just move this one. There, perfect. All right, so that's my matrix there. We can print it just to make sure this is, kind of a more complex one. So we probably want to see there's an error. No. Oh, yeah. So I probably need to run this one first. Let me just do the whole thing, actually. Okay. Run that one. Okay, there we go. So now I have my matrix, no problem. Now, as you might imagine, if you want to extract just a value from a two-dimensional, you need 2 indices. So we can do print. And then we're going to do, let's say, first. And it's going to be equal to A, 0, comma 0. Okay, and that's it. A, 0. And that. Right, so we get number 1. If we wanted to get, let's say, the last one, say I want to get the last one, so we can try print last, and then here I can do A, and then from the last is going to be on the 3rd row, so that's 2, comma, and then I can just say last minus 1. Okay, so if I try that, it should give me 12, and there you go. So you get a 12. And that's it. Now, that's probably a very easy topic that you guys, I'm sure, are quite familiar with. Right, and now we're going to do something called slicing. Okay, so we're going to do slicing. And this is something that is very necessary sometimes. The idea with slicing is that you're going to extract out of the matrix, out of a matrix that's bigger, you're going to extract pieces, but they still could be matrices, they could be vectors, they could be subsets of matrices and vectors, okay? So that's basically okay. So let's do slicing. Create just an array, 15 values. Okay, now let's say I want the first 4 elements. If I want the first 4 elements, so we can do X. And now notice here, I could do 0, 4, right? Or I could do 1, 4. But when I leave this blank, that just means that it starts at the beginning. Similar, if I had set 4 like that, it means it should start at that position 4 until the end. Okay? So either one should work. Okay, so in this case, I just want to extract the first 4 elements. Therefore, I can leave the first one blank. The colon just indicates range until the 4th element. Okay, so then this should be a square bracket and then close parentheses. All right, we can also do print all after 3. So print all after the 3rd one. Okay, and now it's going to be X like that. Okay. We can also do, so this will give us all after the 3rd one. We can also do, now this is, this one is actually could be very useful at some point. Let's say I want all even indices. Right, so I want, let's say that you have a matrix or a vector, and for one application, you want all odd numbers, all odd indices. And then for another one, you want all even, right? So what we can do then here is comma, X. And then here we can say from beginning to end, and we add a second colon to indicate step size 2. So it starts at 0, so it's going to go step size of 2, so that's 0, 2, 4, 6, 8. Okay, so I'm going to write a comment here. I'm going to say starts at 0, and then 2 is the step size. 2 is the step size. Questions? Make sense?
Yeah, it makes sense.
Okay. All right. So good. So let's go ahead. Let's run these actually. Make sure they're running. Let's go ahead and do run. All right, and you can see there, first 4 elements are 0, 1. There's the whole vector. First 4 elements, 0, 1, 2, 3. All after the 3rd one, 3, 4, 5. Yeah. Even indices, 0, 2, 4, 6. And you can see that there. And that's really good because first you get these indices, and then after that you could slice these out of your vector. Okay, so that's really the advantage of that. So let's try another one. Let's try uneven. Let's try uneven. So I'm going to do, probably copy this one. Print uneven indices. And all we have to do is change this, right? So change the starting position. So instead of starting at 0, we start at 1. And the step size is still 2, so it's going to be 1, 3, 5. So we can say starts at 1. Okay, we can run that one. You can see there 1, 3, 5, 7. Now, let's say that I want in reverse. I want the array in reverse, so I can do print reverse, comma, and then I'm going to do X, and I'm going to do from 0 to from beginning to end, I should say. but the step size is -1. Or yeah, that indicates actually the step value is negative, so it starts at last element. It kind of implies that. So if I do this one, you can see it started at 14, and it just worked this way down from 14 to 0. Okay. All right, so let's look at now. I think that's all with slicing like that. Now let's look at slicing from a bigger matrix, a smaller matrix. All right, so let's say that I have still slicing, and I have A equal NP array. Same thing. I'm going to do 2 square brackets. And then within, I'm going to do the individual square vectors. So I have the first one, comma. It's going to be 1, comma 2, comma 3, comma 4. And then can't get that one to. All right. Yeah, I think better there. All right. So then 5, 6, 7, 8, comma. And then the last one will be 9, 10, 11, 12. And that looks correct, I think. All right, so now we can do print A, so we can see the whole thing. And then let's just slice a smaller portion. So we can say A, and we're going to go from, so as far as the rows, we can say I want from beginning to 2. All right, so let's try that. And then as far as the columns, I want from beginning also to 2. Let's just try and see. Usually with this one, you kind of have to try it out a little. Because I don't think it starts at index, but it actually starts at 0, but it starts at 1 actually. So let's do this one. Right, so you can see there, it sliced 1, 2, and 5, 6. So basically, if I wanted all 3 rows, I can probably change it to 3. Run it again, and you can see this time it sliced, you know, the 2 columns of the 3 rows. So it's sliced 1, 2, 5, 6, 9, 10. Okay, so that allows you to manipulate your vectors and matrices. So this is good because whenever you're doing things, you know, it's good to be able to think like this before you start. Oh, I'm going to write 2 for loops, iterate, find these values. Well, you know, I could probably just slice it out of the matrix. So that's the reason why I wanted to show you this before we did a lot of the algorithms, and in particular because the KNN algorithm is actually in Numpy, so that also I wanted to make a little bit more sense. But I think, you know, I'm sure you can see the value of this. And I can't stress enough how important this is, because everyone else, PyTorch, TensorFlow, they have all modeled their approaches on this approach. And it's actually funny because this is just MATLAB. So MATLAB was a thing, you know, you guys, you know, everyone keeps telling you guys, you learn stuff and then by the time you graduate, it's not even the principles are relevant, but the technologies are going to have changed so much, right? And that's very true. Like, when I was a student like you guys, all we had was MATLAB. And everything had to be done in MATLAB. MATLAB is still around today, and they're still a powerhouse for some things, but they have been replaced. It's definitely in the AI machine learning area, they've been replaced. I think in like engineering, I'm sure mechanical engineering or something, they still use it a lot. But some trivia there. All right, so let's keep going. So let's do. Let's just do. So we slice that. We can also slice. What are we going to slice here? Let's just play with this data actually. So I'm going to take A, which is still the same 1, 2, 3, all the way to 12. Continue to use that one. I'm going to print it again. Print A. Then I'm going to print this. So this should be, so let's say that I wrote A, you guys tell me what you think this will do. So A from the beginning all the way to -1, comma, from the beginning all the way to -1. What do you guys think this would, don't run it, just what do you think this would return in your opinions?
I assume it prints every row in every column.
Why?
Because -1 is the last element.
I can't hear you, Ryan.
-1 is the last element, so I would assume it goes from the beginning to the end.
From the beginning to the end, right? But isn't that what this is for?
True.
Sure, right?
Yeah, I'm not sure.
Then, well, -1 is what? The last index, right? We talked about that, how it's the last index. Like if we go, where was it? Yeah, the last one, right? 2 and -1. So it's actually, this is an interesting one because sometimes, as it turns out, you want to look at all the values except the last one. Let's say that you're trying to shift numbers, that's, shifting, right? So shifting the numbers, like shifting one row, one to the left. And so this comes handy there because this will go from beginning all the way to the element before the last. That's what that does. So if I run this, you can see there, it went all the rows except the last one, and from the columns, all the columns except the last one. So it did 1, 2, 3, and 5, 6, 7. Do you guys see that?
Yeah.
Search to filter out the last element, last index. Okay, great. All right, so let's keep going then. That's a useful one. As I said, a lot of these things, what I have done over the years is I have collected a lot of these things out of algorithms, right? So there's this little piece that, and I always, so I've accumulated them here in a way, in a sense. All right, so let's take a look at, that, we can repeat the exercise just with -2. So if I do -2, then what would the matrix look like then?
So then you want to print the last two vectors?
Think about it, right? So it goes, how many rows? The first two, right? That didn't change. Same thing with the previous one. But here, it doesn't include the last two what? Columns, right?
Oh, columns.
Okay. So then the output really should be 1, 2, 5, 6, right? So it should be 1, 2, 5, 6. 1, 2, 5, 6. So let's see if that's the truth. Yeah. So there you can see it's 1, 2, 5, 6. You see that? All right. So good. Okay. Here's the example that I was telling you about, shifting. So shifting is actually pretty interesting. Let's say, for instance, that I wanted to, just think of this scenario. This is a machine learning problem, right? A natural language processing problem. Let's say that I wanted to translate. Translation in the last 2-3 years has made a huge leap in research. You can basically go to YouTube now and see their auto-generated translation. They're really good. Not to mention their text, their speech to text is also like scary good. I do a lot of these videos, and I post them on YouTube, for various things, courses and stuff. And we never have to put in closed captioning. We never have to put the closed captioning in there. I mean, it just automatically does it. I don't know if you guys knew that, but that to me is pretty incredible. All right, so
I was going to say something interesting. I used to work in the OIT office, and we had to subtitle the commencement address, and YouTube's algorithm to subtitle stuff was better than what we paid for separately. So we wound up just switching to posting the videos on YouTube because they were more accurate with subtitling, and then we just corrected the things there.
perfect example. I mean, literally, like I had a project where I had to do this course for like a business, and it was part of the budget was that what you just described, and literally we just discovered put them on YouTube free. So it's incredible. And now translation is the next level, where because they take that text, you don't translate directly from the speech. You take the speech. English will probably be the best. Just because, I'm sure they put in so many resources to that. So they'll have the best speech to text and then take the text and convert it to any language in the world. There's something called the transformer model. I know it sounds, like Transformers, but it just means it transforms. The data gets transformed like we're doing right now. We're transforming data, slicing data, you'll see that. So anyway, so the transformer model, which is a very deep learning algorithm, the kind of deep algorithm that you can't do on a laptop. And they were just invented, I mean, literally like discovered or created fully efficiently in 2017, 3 years ago. And they just, oh, wow. They're pretty incredible. And one of the problems in that algorithm is that you have the following. So the cat is sleeping, right? And that would translate, let's say, to Spanish, el gato está dormido, right? So you have, I misspelled it. So you have basically this, and you have these 4 words, and sometimes, an English sentence might be 4 words, and a Spanish sentence might be 5 or 6, right? So, or French, or I don't know, other languages. And so the problem is doing this, translation. But sometimes what you want to do is you actually want to shift these, because what the transformer wants to do is it wants to predict the next word in the sequence, right? So it wants to, it can't look, when it does the training, obviously it looks at these 2 sentences, but when it does prediction, obviously, it will only have this one, the cat is sleeping. And so it wants to predict the very next word given the previous word, okay? And so what it might do there is that it needs to look at the current English word plus the previously predicted word. So really what it should be doing is something like this. You see, it shifts the words so that, or maybe, let me put it, oops, sorry, like that. You see, because here, that's where the real is happening, but in reality, these, in the prediction, they're not there, right? So let's, something like start of sentence, there's a special character so that the vector is fully aligned. See that here, sort of like that, right? And then end of sentence would be the last one. So this one aligns like that. You see, so that's basically all I did is I shifted one word to the left or the right. And then when the model predicts, it should predict everything and end of sentence. So it looks at the English sentence, whatever it is, and then it predicts some word, right? And it kind of follows this. I want to say I have these mixed up. Might be, this one is start of sentence. Yeah, I think so. It's like that actually. Sorry guys. So it's this, and then get rid of that. Right, and so anyway, better. It's like this. I'd have to look at my notes, but yeah. So, and so they've shifted. So they shifted all the words to the right ones, and then you kind of have to predict these. You have to predict these. So I look at the. I know I'm at start of sentence of the target, and so I predict it. So hopefully you predict el, right? And then now you look at the next word, cat, and you know that you predicted this, L. So that's really where that goes in the prediction, not in the training, in the prediction. So you just, right now, just for reference, I have this in here, but imagine it's not there. So then it looks at cat, it looks at L, so it knows L, the, well, a determiner is usually followed by a noun, so that narrows the probability. And then it says cat, could say dog, I guess. So then that becomes, oh, sorry, in Spanish, gato. Right? And that becomes the word that you have on here. So now you have is. You know that the previous word was gato, right? So, okay. So now you have a noun phrase, probably a subject, and then you say is as a verb. And so this, and so on. So that's, that's sort of, I wanted to give you this because usually I actually added this shifting in here because of transformers as some help. If you guys ever take the deep learning class at the graduate level, you'll see that there, and it'll come from here. So anyway, so to do that easily, part of the algorithm requires you to do some shifting efficiently. And so shifting can easily be done with what you're learning, which is this idea of slicing and shifting things around. So let's play around with it a little bit. Oh, there's a question. So would that be like how Grammarly processes and detects sentences? If you mean translation, the state of the art right now is transformer models.
Well, the question was because you were looking at the previous sentence and you were saying, "Oh, cat." So the next one, is like sleeping or is because of the nouns and whatnot. Do you know like the Grammarly program?
I mean, I don't know the particulars of Grammarly.
It's just like a grammar fixing like site that just
Oh,
looks at
oh,
what you
I see
type.
what you're saying. So your question is, I get your question now. It's not about translation.
Yeah.
It's about grammar correction. Does grammar correction work the same way? That's what you're asking, correct?
Yeah.
Yeah. Grammar would be, so in grammar, you don't have two languages, right? So it's different in that sense. In what I was showing is you have two sequences of tokens, right, that are must be aligned. One must generate the other, right? That's translation. I give you a sentence like in the problem you're watching your favorite show on YouTube, but it's in, I don't know, some other language, right? French. And you want to understand, you don't speak French, but you want to understand it roughly. So you can auto generate that. You generate two sequences. Grammar is about predicting the sequence of words. So actually, when we do not, we're gonna do a little bit of naive Bayes next week. We'll see those sequences. Also at hidden Markov models, we'll see those sequences. There's a difference though. They are sequential models, but they're more probabilistic, right? So they're gonna look at, okay, currently I predicted this. You know how it might be similar though? It might be similar in the sense that it looks at the word and it also looks, you can do, you know what part of speech tagging is?
Not specifically.
Remember, so you learned that in school. Part of speech is just like the is a determiner.
Oh
Calix,
yeah, like the articles and whatnot.
those are parts of speech. And so imagine it might be similar in the sense that instead of translation, what would this have to be? DT, right? What would this one be? Noun, sleeping, verb, and so on. Do you see that?
Yeah.
So there is a similarity there that you can take the words by the frequency of what they are. You can say if they are determiner, noun, verb, etc., and then use that information together to correct grammar. So in a sense, yes, it could be a little bit similar.
Okay.
Answer your question?
Yeah, no, I was just curious because as you were going through it, I was just wondering if they correlated.
Like I said, in English to like another language in translation, when I've worked on this, I didn't have to do part of speech.
Okay.
Just needs the words. It uses a mechanism called attention. It just uses the actual vocabulary. But in grammar, I can imagine how I could use information like the words themselves, but also if they are, what part of speech they are.
Okay.
All right, good question. So now let's do the shifting here. So I've explained kind of the intuition as to the why, right? So you don't just like see a whole bunch of exercises there. Now let's create, just a sequence of 15, right? So we do 15 here. We're gonna print X, right? So you can take a look at it. And then we can do, now we're gonna shift the data. So let's take a look at it first. So there it is, right? And then we need to print them sort of aligned. So I'm gonna do print. And you'll see how straightforward. Imagine how much work you'd spend doing this, like in a for loop or something. So take a look at this. So just shift right. And that's going to be X. And this could be, like a good exam type question, right? I just ask you to shift them. So here, -1. right? So it goes from beginning to -1, and then this one goes to shift left. And then we'll play with the spaces so that they look aligned. And then this one could be from 1. Notice it doesn't, it starts at 1 all the way to the end. Okay? So now if we print the, oh, I'm missing this script. All right, so if we print these, let's take a look at what they look. You can see that I probably should have done this. All right, I have my 3 here, so I probably want to align them a little bit better. All right, good. So do you see, we have the original one, and then now we have the same, right? And all the values in the other one have been shifted. So notice 0, 1, 1, 2, 2, 3, 3, 4, and so on, 12, 13, 13, 14. Do you guys see that?
But the first one doesn't shift anything to the right. It just removes the last number.
Right. But it represents that. You could always play with it a little bit more. And
Okay.
if you don't want to lose values, you can add special characters at the end. And there's something we're going to learn called concatenate, which will allow us to concatenate another vector to the left or to the right. And so to put in those like end of sentence, start of sentence, because here we did lose one value, the 14, right? But do you see how this works, guys?
Yeah.
So that's basically the idea there, and that can be very useful. Remember that usually you have data, but what you want to do is you want to shift, the indices and then slice out the data. Or here in our case, we have 2 vectors, so it was pretty easy to just shift them. So this just represents what we're doing here. It did technically, so the bottom one did technically shift to the left because it's like a tape, right? We lost the 0. And in the top one, yeah, that one may have not. Basically there was a shift in them. All right, that's shifting. Now we're gonna get into columns and vectors. Sorry, rows and vectors. So, sorry, rows and columns. But what we want is vectors from a matrix. Okay, so to do that, then let's just grab that same matrix we've been using. This one. Okay, so that's our matrix. 1, 2, 3, 4, and now we just want to slice out a column. Now this is something that you might need to do. All right, so we're going to do print, and you want from that you want what do you want? All right, so let me put it to you guys. I want you to slice out column, the second column, 2, 6, 10. How do you do it?
It would be the first, which is a bracket, then colon, and then 1, and then comma 3. No, so like in the bracket right there. So that should be a 1. The comma, no, where the comma is should just be a 1.
If that's a 1, it'll only slice out 0. You actually had it right. It's all the rows.
Oh.
It's all the rows, right? Because you want all the rows, but you only want column
1. Okay.
That's so you want. Think of it as the indices, right? I want this one, and this one, but only of column 1. So that's why you do colon all and 1. You see that? So if I run this, I get 2610. As I said, with these things, don't worry about memorizing it at all. Just have a feel for them, and you always have to, okay, how do I do this? And then try a few things until you remember the correct one. Now, if I want to do row, let's say I want row 5, 6, 7, 8. I want 5, 6, 7, 8. How do I do it?
Just comma 1 colon.
Comma 1 colon. That gives me from the well, actually, if you want all the columns, then it's like that, right?
Oh.
And here, now here you're missing something. So you need to have something in here.
Well, you only want the second row. Should the 1 be there?
1.
Okay.
Exactly. Right, 1, right? Because you only want 0, 1, 2, 1, and then all the columns, right?
So a comma tells you only want this one item or this one indice or whatever.
Comma separates the I's from the J's.
Okay.
Right, so to the left of the comma, you're talking about rows. To the right of the comma, you're talking about columns. So here, adding the colon means you want all the columns. Adding a specific one means you only want 1. You see that? And the index, actually. So if we run this one, did I run it? There it is. 5, 6, 7, 8. So I've got my vector that I wanted, my row. Okay, remember that's an important operation. Okay, let's see what else. So let's now shift gears a little bit and let's talk about the let's talk a little bit about the what are we talking about? The KNN algorithm. So let's take the rest of the class today to just focus on the algorithm. We'll come back to these later. Probably even there are some somewhat advanced topics like broadcasting, which I will probably not cover in the beginning as it relates to Numpy. But I think right now, I would say you probably have a feel for it, right? You have a feel for how it works. My suggestion is practice these, okay? I provided the link where you can find on my GitHub all of these examples. Practice them, play with them. We'll come back to more of them. But now, I think I'm going to save. And then I'm going to create a new Jupyter. Oh yeah, that's just insert cell. New, I think this is, nope. New notebook, there we go, Python 3. And I'm gonna name this one KNN. KNN NumPy, so that it's, because it could be KNN just with for loops without the NumPy array. You could write that, but it won't be as efficient as this one. Remember that I will give you just the algorithm, but I'm not going to give you the data, right? But in your homework assignment, which probably it'll be due a week from Wednesday, I think that should give you enough time. Now you know how to create data. I pointed that out at some point. You'll have to figure out how to get your own data and do the analysis. I think on Wednesday also, we'll cover a little bit of performance metrics. So that should give you a little bit of intuition for the whole pipeline. Okay. So so everyone with me, we're gonna do now the KNN algorithm. Okay. All right. So let's go ahead. And I'm just going to create, you could create a class, you know, do it object oriented. Give me a sec. Let me get some coffee. Okay, so we could create classes, and I strongly, I strongly recommend object-oriented programming in when you do this kind of work. I don't know what that was about. Okay, so you guys are seeing this, correct? You're seeing my notebook. Okay.
Yes.
This one I don't have on my GitHub. I don't actually have this algorithm, so I need to post it. Okay, so just remind me of that. That I need to just like insist if I forget, or email me that if I forget to upload this. Now I would recommend that you, and I'm actually going to write all of it in one single cell. So let's say you could do something like this, right? You could do a class KNN, call it my KNN. You guys know that, define things, the constructor, everything. I strongly recommend that you do it that way. Okay, I'm only going to give you pieces like a Lego puzzle right now for you to put it together. Okay, and then but I do recommend that you take this approach. As a lot of code nowadays, machine learning, deep learning code is written very much in object-oriented ways, and so you know you don't want to fall behind. All right, so let's say that what do you need? You need K, right? You guys remember what K was, right? So let's say 5. It's an uneven number. It's the number of vectors you're going to compare to. Also, you need, and I already gave you this, the Euclidean distance. However, I gave you the Euclidean distance, I think, with a Numpy approach. And then here, the only difference is that it's going to be with a Numpy approach. So remember, it takes 2 vectors usually, right? 2 points. So let's say, remember that a vector is a point, and you can call it V1, V2, for instance, and that just means vectors 1 and 2. And then, you know, just, I like this function because it's actually pretty easy and simple. It might take you a while, but think about it. All we're going to do is, we are going to, if you remember the intuition, we went over, if you don't remember, go back to that video. We did all the, like a little bit of the math, and we even wrote the code. So basically what we want to do here is we want to take the 2 vectors, V1 minus V2, take the difference of them, right, in the algorithm. Now, this will do it on a element wise, right? So it's gonna be, what that means is that you don't have to iterate through all the elements in the vector, right? Because that vector might be F1, F2, F3, F4. So it actually could be, you're doing something like this. You're doing, you know, let's say 2, 5, 7, 2, minus 3, 5, 6, 2, something like that, right? So you're taking the difference between these. When you have two vectors that will have the same dimensions, right? So they're both R4 because they have to be, 2 points in the same vector space have to have the same dimensionality. You don't have to iterate and say 2 minus 3, 5 minus 5, 7 minus 6, 2 minus 2. And that is called, instead, you just do the operation on the two vectors, and it's going to perform it. We'll see that in a second. This reminds me that I should probably cover operations. So we'll cover operations in a sec. And this is called element-wise. Okay? And it'll perform the operation for you. Okay? So let's just, the point is, although I wanted to cover that in the NumPy, I want to get this algorithm out of the way. So let's go through the algorithm. You will then, we'll go after this, we'll look at those operations, element-wise, etc. You know, multiplication. Yeah, I realize that I have that in my handout. It's just way at the bottom. But let's get the algorithm out of the way. At least you have it. All right, so V1 minus V2, right? So we've got that. Imagine it does it element-wise. This, I think I already showed. This just raises something to the power of 2. If we did this, you know, it's like square root, right? So 2. This is also in parentheses, right? So I'm just kind of building the intuition. So we've built that already. And then those elements that have already been, they're basically element-wise, the values have been taken the difference and they have been squared. So basically you have the elements, you know, it's almost like this. So this one is, it's gonna be maybe V1 minus V2 1, right? Squared. And then you have comma V1 2 minus V2 2, and then the result of that squared, and then V1 3 minus V2 3, right? So they're you know, you're taking elements from each one, taking the difference, squaring them, and then that just gives you the result of this you need to add. So we're going to add the result of this plus the result of that plus the result of that. And that's where we're going to do NumPy sum, right? So that way now, look, we've got the operation there. And then the result of all of that, if you remember the equation, was to square root. So we're just going to do this. And then do NP dot square root. And don't worry, like if you know, we'll come back to this. Obviously, my suggestion is run this function on your own. Obviously, play with it. We'll come back to it a little bit more, but at least now we have a NumPy version of the Euclidean distance. Make sense, guys? Any questions? No questions?
Makes sense.
All right, so well, you know, as I said, these are the tricks that we have to figure out. But we'll come back to this idea in a second. All right, the next thing that we need is our data, right? So this I'll leave to you guys. You will have an X matrix. I already showed you how that works. And you will have a Y vector, right? So the Y vector has to have the label. So I suggest you create a data set, 100 samples, whatever. You know, at least 30 samples would be enough. have two classes, whatever you want them to be, 0 and 1, and then your data, obviously, however many features. So 30 rows would be 30 samples, and then you decide how many features you want in there. All right, so I have the data. So the next thing I need is I need the, you know, that's, if you think it's not really that complex, right? So what I need now is I need two functions. I need, or actually, what do I need? I need, there. All right, so there is another thing I should say with KNN is that KNN is what is called a lazy algorithm, right? What that means is that there is no training beforehand. Instead, you just have the data and then you run it. So there's technically no need for a training function and a testing function. That's usually, in most of machine learning, that's what you have. You have a training function, right, where you train the model, and then you have a test function where you apply the model. Here, there's no need for those. We really just need a predict function because the predict function looks at all the data. So it looks at all the data, calculates the Euclidean distances, and then it sorts it and then it selects the label. So that's really all it is. So there is no need for a for that. So let me, I like to add these lines, kind of separate the code out. It's just my preference. All right, so now I have my data here. And now, so we only need the predict function, right? So we're going to define predict. And we want this to take some parameters. The advantage of having made this into an object is that, you know, passing the data would be a little bit easier. So let's see here. I have, all right, so let's think of the intuition. I want, I want to predict. So let's call it ypred, right? For remember, you have the idea of a given sample, right? So you have the idea of a given sample. So let's say in a list, I'm going to create a list and I'm going to say for x in x, right? So x, the big X is the whole data set, right? And then this loop, my goal here is to grab every single row. Remember, so if you have 30 rows, it'll do this 30 times, okay? So you iterate, grab the row. So, you know, for x in x, grab the first row, the second row, the third row, the fourth row. So that basically means that you're grabbing all the training set, right? And you're going to compare. And you know by index what position you are in also tells you what label is associated with it, right? So then I have my X, and the question is, what do I do with it? So for each element, now, let me think about this. Let's do. Actually, let's call this X train. I think. No, I don't think it's necessary. So just for X, what do I need? I also need in predict. What do I need? I need the test sample, right? Test. Let's call it test X. Actually, that would be a good. So now I have test X, and I'm going to compare it to all the elements in X. You see that? So then in here, what do I have to do? I have to make a call I have to compute the distances between X and all examples in the X training set. So maybe I should write that. So here, calculate distances between test X and all all data samples in X uppercase. So now here then I can call the Euclidean distance function. So I can just say Euclidean distance, right? What are the two parameters that should go here? Well, should be test X, or test underscore X, comma, because it takes two parameters, right? V1 and V2. Test X, and it also takes X. You see that, guys? Does that make sense? Maybe I think, those X's look a lot alike. So I'm after all of them. All right, so that should be better. So now I'm iterating through this. This is called, hopefully you guys remember, this is called a list comprehension. A list comprehension is writing a for loop in a one-liner. And it just makes your code a lot more succinct, right? So I have the for, the result, so I do for X and X. This X that would go underneath here is this X here. And the result of the Euclidean distance will basically be, for that test sample, I'm going to take that test sample with the training data, calculate all the distances. So there's going to be 30 values in this list. So this will result in a list. Is this clear, guys?
I do have a question. So you have test X and X. Is that going to be split from X, or is that just a different vector in itself?
This one, so a list comprehension is, you know this, right? So if I do for X.
Well, yeah, no, that's not my question. My question is for the Euclidean distance formula or method. You have the two variables, which is the test X and the X. So I'm just saying, is the test X going to be a new matrix that you're creating, or is that just going to be a split from the X train?
It's it's a vector. So you need to create it. Maybe I should.
Okay.
It's your test vector. So for instance, let's say, the stock market, GameStop, right? You guys have been doing all the way to GameStop. So you have all the GameStop data that the hedge funds and Reddit, they all have this GameStop, features. They created their data set. Now, tomorrow, you get some data, right? That the model, the model was built last week, but tomorrow you get some data. It's your test sample, and you just want to know, should I buy or sell? So this is tomorrow's just one vector, and you compare it to all your trained samples, and then you calculate the distances between, let's say your data set has 30 samples. This is just one, so obviously you end up with 30 Euclidean distances. Does that answer your question, Josh?
Yep. Thanks.
So that's what you do, right? So for X and X train, and then you plug in test X, which is coming from here, and then kind of the data, you just have it, and then you take the Euclidean distance, which is, of course, this one. But all of these things are vectors. That's what I want you to, and I want you to define that, Maybe think of GameStop data and try, that would make it an interesting problem, right? So what would be the features there? So this would be Fn, and then these matrices, remember, are gonna be two-dimensional. So let's say 30 samples, and then a vector of F1, comma F2, 3, comma dot dot dot. Right? So that's sort of how it works. So now we've got the distances. So remember that the output here ypred is a vector of distances. Ypred, at least at this point, is a vector of 30 distances, because that's what you have in your data set. Okay? So now that we've done that one, what else do we need? We've calculated the distances. So what's the next step? The next step is probably sort, right? If you remember the algorithm, we discussed it in the lecture, and I gave all the details of it. So you do sort, distance, sort by distance. So sort by distance. And return the k. Remember, k is 5 over here. It's a very important value. The k closest neighbors. That's why it's called the nearest neighbor algorithm, right? So it looks at your closest neighbors in the vector space. So you're going to sort it. And so that, because NumPy is so great, that's easy to do. So let's call this one sorted. No, let's say k, right? So these are the k neighbors, because it's only going to be 5 or so. So we could do, we take, what did we call it? We called it, we should probably call this distances, actually. I realized that might be more intuitive. All right, so distances. So we're going to take the distances, right, that vector, and we're going to apply a sort. And NumPy has arg sort. Right, so arg sort will now take the we'll look at the distances, right? And we just have to think about what arg sort does. So arg sort should so let me write over here, arg sort does not actually return the distances anymore. It only returns the indices. So arg sort returns the indices of the k neighbors. Here. So do you guys understand that, the difference? So for instance, you know that in distances, right, in the vector distances, there are 30 distances, which are aligned with the 30 samples, right? So they're aligned with the 30 samples. So it might turn out that this one, I'm just making up some numbers. So it's 23, 2, 145, 23, or 24, 5, 17, A990, ... until 30. So it's going to sort these, right? But it's going to sort this. The answer will be that it's going to give you the indices. So it would extract indices like this one. So if this is 0, then one of the answers would be 1, probably 4, and so on, right? So it would give you 1 and 4. Those are the shortest distances. And it's going to give you those indices. And that's useful because now you have 1 and 4. And in the Y-train vector, you can just look up, okay, what is the label for 1? What is the label for 4? And boom, you're done. Is that clear, guys?
Kind of.
Kind of. All right. So let's see here again. So those are values. These are indices. These are indices here.
Well, that part makes sense to me. What I was the kind of was the Y train. So the Y train is going to say like.
Okay, so you understand that K neighbors is going to give me just the indices, right? So I have,
Correct.
let's say I have 1 and 5. 0, 1, 2, 3, 4. So I have 1 and 5, right? Let's say that this is 1 and 5 here. But I know those are the indices that and there's 5 of them because I'm going to take the top 5 shortest ones. So what I can do now is I can go into Y train, and Y train is size 30. It's 30 by 1, right? Because it's the classes. So all I have to do is I can do Y, and you can provide in the slice a list. So I could just provide K neighbors, and it's only going to return the labels for the matching one. So it's almost like it's going to do this. So it's going to do Y1, and I get that value. And then it's going to do Y5, and I get that value. And those, remember, the Y contains the classes. So for instance, for the GameStop problem, it would be something like buy stock, sell stock. So it might turn out that all 5 of these say, or 4 of these say buy stock, 1 says don't buy stock. Therefore, 4 wins over 1 is a voting rule, so you buy the stock.
So my question is the Y train. So like this, because is this the whole algorithm or is there more to it?
We're almost done.
I'll wait for my questions to the end.
We are almost done with this one. That's what's so great about this is that such a simple algorithm. All right, so I do the arc sort, right? Which basically means I sorted the distances from shortest to highest. Okay. Now I have them sorted. So I know they're gonna be now, but instead of returning the values, remember, instead of putting 2, 5, 17, 23, 145, 890, instead of returning that, which is what you would usually associate with a sorted array, it returns the indices of them, which is really valuable. Now, there are other ones that will give you the values, but in this case, what we want really is the indices because, as I said, that makes slicing out of Y train extremely convenient. Now, this NP-arc sort distances currently has all the values. All 30 are in there. Now they're sorted by index, but all 30 are there. However, we don't want all 30. We just want the top 5. And to do that, we do a little bit of a trick, which, again, is slicing. So imagine the result of this is a Numpy array, right? Which it is. Imagine that whole thing is a vector of size 30. It's a Numpy array. So technically, you can view this as A. And whenever we learned that whenever we wanted to slice something out of A, we just do that, right? So it's the same thing here. You don't have to assign it to the variable and then slice the variable. You can just literally here at the square brackets and then say, I want everything from beginning to K. And that way, I just grab the first 5. Is that clear, guys?
Yeah.
Another way I could have done it, but it would have taken 2 lines of code, is to take this. You know this is like A, right? And so I would have done the same thing, but, doing it like that. But that makes the code twice as long, right? So this one just allows me to slice the result of the 30. So remember, it's gonna be this NP-arc sort returns this these 30, but only the indices of them sorted. So 0, 1 would be the first one, and then 4, and then whatever. And out of that, but we still have 30. We really just want those first 5. So then we go from beginning all the way to 5, because we know that 5 is K, sorry, K is 5, which is our K. That's the value that we said. We could have also picked 3. And now we have the 5 in, we have the 5 shortest distances, and in particular, we have the index for them. So actually, I should probably call it K neighbor indices, so it's more obvious. And now the question is that I have the indices. I'm almost done, right? I'm almost done. And now I need to extract the labels from Y. So we could probably say extract labels from Y, from the Y vector, Y train, sorry, Y train. From Y train. And this part, I think, should be pretty easy. There's a couple of ways I can do this. I'm going to do it the non-Python-y way, in a sense, or the non-slicing way. It's still Python. So I'm going to do labels, right? Let's call them labels. And let's do another list comprehension. And that way now I can iterate. So I'm going to do for I in K neighbor indices. So K neighbor. So that allows me now to grab from those 5 that I have in that vector, I can grab the index. And now the result is to take whatever that label is given the index. So I just plug in I, and that's it. This will return my 5 labels. So now I have, imagine that you coded your class, right? So 0 and 1 or some value like that. Now you just have, so this hopefully, let's say, you know, imagine labels is now equal to 1, 1, 1, 0, 1, right? So the majority of the samples that were k-nearest neighbors were of label 1. And there was only one of the 5 k-nearest neighbors that was label 0. And that's it. So then you go, it's like, you know, a voting rule. So the majority wins. So then the assigned label for test X will be 1. Does that make sense, guys?
Yeah.
Now let's call this one. Let's do select the most common label, right? In labels. So you have to select it. So that's the last part of it. So how do we do that? There's a lot of ways, right? There's a lot of ways that you can do that. Trying to think what's the best way. Probably we can use something called the counter. So let's go over here. The counter is a very handy, we'll probably use this again, I'm thinking, for Numpy. Anyway, so let's do from collections. This is a built-in library. From collections, import counter. But, you know, as you know, you can literally, there are lots of ways of doing this. This is just, I think, one of the easier ways. And then we can just call counters. So we'll say most common label. And this is technically widespread. I mean, this is really the predicted label for that test sample, but we can call counter, and then counter then will take in labels, right? It'll take labels, and it's got a built-in method, most common. And you can try that. I think sometimes you have to specify some parameters here. Play with that. But that should be it. Now you have most common label, and that can be your widespread. So then you do control copy. You're going to return this. That's your label right there. Plug in a 1 here. And then now, whenever you want to run this, obviously you'll call predict. So you'll have your test X, right? And your X. And so now you just go down here and you say, oh, I want to predict. And you could do this for multiple samples if you'd like. Like that. And that's it. Oh, so this will return something, right? So then maybe print. And that, believe it or not, is the KNN algorithm. Look at how simple it is. And in particular, because we do it with Numpy, it's even simpler. If we weren't doing it with Numpy, it might be a little bit, not too much, a little bit more. Any questions, guys?
Yeah, I do. So KNN only ever returns one answer as a result.
Remember, what we're doing with KNN is we're trying to predict labels, right? It's a classifier just like any other. So it takes a test sample and compares it to all the train samples, right? And then it gets the Euclidean distance for all. Then it sorts them to get the shortest distances, select the top 5, but select not the value, but their index. And then from that, let's say we end up with something like this. Out of those 5, you take the majority, the most common one, and that's the label. So what we did here is we did this for one sample. Obviously, if you wanted to do this for, let's say you had 100,000 train samples and you have 100 test samples, you would do a for loop, right? So you do similar for X test in, or sorry, for X sample in X test, and then you grab, and that, you pass those to the prediction.
Wait, so for example, let's just say like we have a whole bunch of different pixels of a whole bunch of different colors, right? And each of those colors are assigned like different shades of blue are just assigned to blue, right? So then like the training data, it has like a whole bunch of blue, reds, yellow shades in there. It would just say the overall color of the train is blue if blue is the most appearing.
So I think you're forgetting. So it's only supposed to look at any machine learning problem, not specifically what you say, but remember iris, right?
Yeah.
So it's like, let's take iris for instance. So iris, the famous pictures iris data set looks like this. So it's got, X and Y. And I'm going to divide it, I'm going to split it into, from 1 to 50, 1 to 100. It's got 4 features, right? So this will be 1 to 100, and then this one will be 1 to 50. There's a total of 150 samples, 4 features, so F1, F2, F3, F4. So what you're doing is, if this is your X, right, the train, and then now you just grab one of these. One. That was X test. So in KNN, remember that this is a 4-dimensional space, right? are 4. Therefore, the test sample, this one, F1, this is F1, F2, F3, F4, so the point is there. That's the point right there, the test sample. Now you have all the train samples, all 100. So those are going to be also points, right? So they're points. But each one of those points is associated with a label. So then when you do KNN, you take the distances of all of them. But you only care about the shortest 5, right? And then so you look up those shortest 5 by looking up the distance, and it turns out it's this one, that one, that one, you know, that one. Those were the 5 distances. You take out whatever these indices are, and you slice them out of the y, and that becomes, based on the majority, that becomes what you assign to that blue dot. What the data is, if you were talking about images, for instance, you know, the pixels would be the features, right? And then, you know, that's basically the only difference. The labels, I don't know, cat, dog, blue, green. Josh, do you understand what I said?
I kind of, but my question is for the training data, because it seems like we're feeding the entire 50 rows into the training data, but it only spits out one label for the entire 50 rows. That's where it's not connecting for me.
About this, right? The 50.
Yeah.
Okay. So we, in the algorithm I just wrote, it only does it for 1.
Oh, okay. So I think that's my issue then, because I was thinking it was for all 50.
So let's say that this one is called, good question, this one is called X test, right? And it's got 50 samples, right? So then this, and that would be an uppercase X. So if we go back to our code over here, we would have to do like this. We would have to do, just like we did over here, we would, first of all, we would have to have an actual X test, right? That has the 50 samples. You see that?
Yeah.
This is a, you know, let's say 50 by 4. If you compare it to that iris data set, so 50 by 4. And now you have to get every single one and run it. So you would do something similar to what was done here, right? So pretty much actually this whole thing. So it's going to be 4 test X in X test, the matrix itself. This allows you to grab all 50, one at a time. And then every time you give test X, the current one, and you send it to the function which will compare that one to all 100. Then next iteration, you grab the next one of the 50, and you send that one again, and it'll compare that one to all 100. And you
Okay, no, that just makes more sense because I was just thinking we were putting all the 50 in there, but I guess this makes more sense.
made only for 1.
Okay.
Because you have to compare every sample in the test set to all samples in the train set. Every iteration. That's why this is called lazy, right? You're probably thinking to yourself, but what if I have a billion samples? I have to every time grab one of my samples, compare it to a billion, then again, and you might think that sounds inefficient or something, and it is. That's why KNN is not necessarily a big data algorithm, but it's good to get the intuition. Do you see that?
Yeah, no, this makes more sense.
This is train, whatever this is test. We grab one, compare it to all, then grab the next one, compare it to all, then the next one, compare to all, and so on. That's why the function that I did was just for 1, because really you can then just easily, by doing something like this, you can just call the function every time that you need it for an individual sample. And that's actually a good thing. Do this in your assignment. So now, you should have a test set and a train set so that you convince yourself. And I think you have all the pieces. I think at this point, you have everything that you need to do KNN. Got it?
Yeah.
Let me, what I'm going to do is I'm going to, sorry, I didn't mean to do that at all. I'm going to post this Jupyter notebook in my GitHub, okay? Let me actually also be, so I don't, let me just put it also on Brightspace. So I think under KNN, oh, I already had, no, I didn't have that. I need to extend this, right? So this, let me just add that Jupyter first. So check on your end that I uploaded the correct one. All right, so it should be there now. And then also, I will also upload it on the GitHub later. But yeah, that's good. Let's extend this. So this was due probably. Yeah, let's make it the 10th so you have enough time. And that way there's no issues. All right, that's it. So that, oh, what is this? All right, I think I changed it, hopefully. All right, so, yeah. So that's KNN. I'm done with my lecture on it. And now it is just homework for you guys to get it to work. Next class, we will continue a little bit of Numpy again. We'll pick up where we left off. And otherwise, we will start naive Bayes, right? We will start the naive Bayes algorithm probably on Wednesday, plus a little bit more Numpy. Plus, there's a few other things, performance metrics that I want to start talking about so that you can measure, we can start talking about this idea of accuracy. So when we have labels also for the test set, and then we predict something with a model, we can compare the actual labels to the predicted labels and get some score. So we'll take a look at that starting next week, or maybe Wednesday. All right, so we can, if anyone has questions, I'll stay for a couple of minutes. Otherwise, we can stop here for today, and I'll see you guys Wednesday.